Okay, so this is going to be a short video to give some feedback on the Evolution of the Living Earth exam. And we're going to do this in two parts. So this first video will be on part B, which was the global environmental change part of the exam, and the next video will be on the global biogeochemical cycles. So there'll be this video and another video, which hopefully give you an idea about what we're kind of looking for in some of the exam questions that we're asking you to do. If we just first of all give some general advice to all exams, this is not just for Evolution of the Living Earth, but it's a good idea to have an idea or have a look at some of the past exam papers, but I guess if you do that, you'll notice that they're quite often not the same every year. We do tend to write new questions for each year group of students. So we're not really looking for kind of answers learned by rote or a specific set answer to a specific question that you might have had at school. We're quite often asking you to think a little bit more broadly about the stuff you've learned through the whole course in the exams at university. So past papers are good, are useful. They give you kind of the idea of the style of questions that are going to be asked, but they're not going to be sufficient for you to just learn the answers to those and then ignore the rest of the content of the course. So ideas about what you might do about that is you might look more widely for some kind of example questions. You might look over the course, see if you can write some of your own questions on the bits of the course that don't have past exam papers, for instance, or even take past exam papers and rewrite them in your own words. First of all, just to make sure that you understand what the question is asking, but also to give you more kind of, practice questions to work for. You can always ask the lecturer, me, on the discussion forum or in person. Just give us some of the questions that you've posed and see if they are capturing the kind of content that we're teaching in the course, and whether they're a good kind of route for you to go down for your revision. Next. Okay, so I guess moving on from kind of looking for past papers as something to look at for exam revision. Once you're actually sitting in the exam, you might want to think a little bit more about what you're writing down for your answer. So quite often exam questions will have what appears to be quite a simple answer, but then that can be expanded on to get kind of full credit for kind of reading around the course and learning kind of a wider range of stuff than just the in-lecture material. But when you're doing this, it's always important to stay relevant to what we're specifically asking in the question. So don't just go off on some kind of crazy tangent. Ask and answer the question asked, but there's often caveats that can be applied to your answer to give you, I guess, more marks. And it's all about the marks, right? So everyone loves marks. So don't answer something completely different. Make sure that you have addressed the question before you kind of start to expand stuff off into additional material. So just to summarize how well people did this year, so these are unmoderated marks. This is the broad distribution for both parts B and D, so this is the climate and the geochemistry side of the exam. And you can see that some people did very well, some people did not so well, very broad range of marks. So hopefully this video will give you an idea about what we were kind of looking for to kind of move you from the left-hand side of this graph over to the right-hand side of the graph. And always, even though the people that did very well, there's still room for improvement there. But overall, not a bad set of results for you guys. And the other thing I guess I'd like to say is just, it's really important that you guys don't revise right at the last minute. You have to revise material as we go throughout the course, because if you find you don't fully understand something during your revision period, it's too late, okay, for you to do anything about that. So it's a really good idea for all courses in the future to revise as you go along to make sure that you are understanding stuff. If there are past exam papers, or you come up with your own questions, or you want to look through exam videos like this, it's important to do that throughout the course rather than just at the end. So just as an example here, so this is the data from YouTube. So I realised that I didn't post all of the lecture notes on YouTube. Some of them were on some other site with the lecture recordings, but I did ask you to watch some videos at the beginning of the course, and this is you watching those videos here, and then you kind of stop watching them. Maybe that you fully understand the content of those. But I did ask you to start watching the exam revision videos, and there are a couple of those, and you can see that those are these guys over here. Not really watched extensively throughout the whole course of the course. So try and spread your revision out tactically early, so that if you do identify problems in your understanding, you can do something about them before it's too late. So what we're going to do now is just go through the two questions on this part of the exam, the environmental change, so the climatey part of the course, and I'll do another video for the global biogeochemical cycles part of the course. So there were two questions in part B, question 3 and question 4. The first one was about climate feedbacks and forcings, and then the second question here, number 4, was about climate proxies. So just again to look at the mark distribution, so very similar to the mark distribution for part B and B together. Part B was maybe a little bit better, but again there's a wide range of marks. Some students doing very well, still a little bit room for improvement, some doing not so well, but overall most people are passing, which is quite nice. So the first question, question 3, 2 parts. It's always a good idea to have a quick look at the how much these things are worth. So the first part is not worth a lot, it's worth a fifth. And then 4/5 of the rest of the question do the second part. So you really should be spending much more effort on the second part of this question than the first part. So because some people got very high marks on the first part, but they were maybe wasting some of their time that could have been better deployed elsewhere in the exam. So always think tactically when seeing which part of the question you can answer. So we just look at the first part of the question. So part A. Define what's meant by climate forcing and climate feedback. So this is a relatively straightforward type question. So this is a slide from the lecture slides. So you can see climate forcing is something that changes the planetary energy budget, and climate feedback is an interaction within the system that serves to either reinforce or change an original kind of climate change. So just to go through that in a little bit more detail. So a climate forcing is something that's really changing one of these parameters here. So something that's changing the albedo, something that's changing the emissivity the emissivity of the atmosphere. There we go. And something that might be changing, the power of the sun. Now it's really important that when we're thinking about climate forcings, there are things that can change these things over here that are not climate forcings. To be a climate forcing, it has to be independent of the climate. Okay, so it has to be something that is a change in one of these parameters that is not due to climate change. Okay, so an example of something where this is not the case would be melting snow and an albedo change. Okay, so melting snow changes the albedo. Okay, makes the planet less reflective, therefore it'll warm it up. But that's not a climate forcing because that melting of snow is due to climate change. Okay, it's due to getting warmer. So to be a climate forcing, these changes in these parameters over here have to be independent of climate. So so we'll come on to some examples of these in a bit. So a climate feedback still can be something that's affecting these things here, albedo, emissivity, not so much the power of the sun. It's quite hard to change the power of the sun as a feedback. But these are changes in these parameters that are the result of a change in climate. So it could be if it's getting warmer, that might change the albedo in some way, or it changes the emissivity of I keep on saying alphabet. Emissivity of the atmosphere in some way. And the important things to say about feedbacks is they can be positive or negative. Now, some people got a little bit confused when describing these in a little bit more detail when they were saying a positive feedback is something that makes the climate warmer. That is not true. Okay, the term positive or negative when referring to feedbacks is their effect relative to the initial change. So a positive feedback can cause more cooling if the initial change is a cooling. Okay, so it's positive in that it is in the same direction as the initial change in climate. Okay, so that's quite important. Okay, so moving on now to the second part of the question. So using relevant equations, chemical reactions and examples, how CO2 can act as both a climate forcing as well as playing a role in both positive and negative effects. And you can kind of hopefully see how this question is basically just asking how feedbacks are different from forcings in a different way. So hopefully, if you've done well on the first part of the question, you should do well on this part. Again, just kind of rewriting the question just to kind of restate it in kind of more simple terms. How is CO2 a climate forcing? How is CO2 a positive climate feedback? How is CO2 a negative climate feedback? Just write down those examples of those three things, because you have to use equations, chemical reactions, and examples of these things. And basically, if you do that for each of these three things, then that's kind of the outline of a structure of your answer. Okay, so just kind of whiz through these kind of things. So CO2 can be a climate forcing because it can affect these parameters. Okay, so it can affect, well, one of these parameters. It can affect the emissivity. Okay, and it can affect the I mean, that would be good to write in an answer. You could expand on that a little bit more detail by saying why it affects the emissivity, and that's because it absorbs in the wavelengths of radiation that are given off by the Earth's surface because it has a temperature. So that kind of explains how CO2 can act to affect the climate. But again, to be a climate forcing, that change has to be driven by something that is independent of climate. So you could give an example of long-term changes in volcanic eruptions. Okay, so these are, if you change the seafloor spreading rate, you're going to change the global rate of volcanism. Those volcanoes add CO2 to the atmosphere, and that change in the amount of CO2 in the atmosphere, nothing to do with climate. Okay, so it will cause a climate change, but it is not driven by a climate change. Okay, another example might be the carbon that we've put in the atmosphere by fossil fuel burning. Okay, so the carbon in the atmosphere, okay, kind of is the forcing, but I guess more strictly speaking, the forcing is us burning fossil fuels, because that's not dependent on climate. The effect of that is CO2 being in the atmosphere, and then that affects climate change, or makes the planet warmer. So that's the kind of thing we're looking for each of these kind of items in the question. So that's the forcing done. How is it a positive climate feedback? And an example of that might be the solubility of CO2 in water. Now, the important thing for this being a feedback is to mention that the solubility of gases, specifically CO2, is proportional to the temperature of the water. So that allows climate, through temperature, to have an effect on the partitioning of carbon dioxide between the atmosphere and the ocean. So in this case, it would be good to mention that. You could use equation for Henry's law. You could even maybe draw the graph of temperature solubility, or mention that there is an inverse relationship between solubility and temperature. Similarly, for the negative climate feedback, you can start to use some of the equations that demonstrate when weathering happens, that draws CO2 out of the atmosphere, either as just carbonate weathering or silicate weathering, depending on whether the weathering and the precipitation of carbonates in the ocean is in balance or not. Now, for it to be a forcing, though, for it to be a feedback, okay, weathering has to be controlled by climate. Okay, so if you change climate, you can change the rates of weathering, because the rate of weathering is a series of chemical reactions that would be dependent on temperature. They also need water. Precipitation on land is correlated with temperature. When the climate gets warmer, we have more weathering, we reduce the CO2 in the atmosphere, and it is a negative climate feedback. Okay, now, in this case, weathering is described as a feedback, but that's because the changes in weathering that we're proposing are driven by climate change. You can also think of weathering as a forcing, okay, but only if the changes of weathering are not driven by climate. So mountain uplift, for instance, might change the rates of weathering because you grind the rock up in small pieces. But in this case, that would be a very poor answer to this question, because if you used that example, you would have to use that example as CO2 as a forcing, okay, because in this same CO2 is a forcing through weathering driven by mountain uplift, which is totally independent of climate. So it was a little bit tricky answering some of these questions, because some of your writing was a little bit confused in between kind of when you were talking about forcings, when you were talking about feedbacks. You need to be quite clear, okay, in this kind of question, because it is quite because CO2 can be all of these different things. It can be a forcing, it can be a positive feedback, it can be a negative feedback. If we're asking for examples of when one is each one of those specific things, then you need to be quite sure that you are talking about the right thing in your writing. Okay, so clarity of writing is important, as well as your knowledge. Okay, and you could kind of go on to elaborate a little bit more about examples of how the mechanisms of a feedback work. If it gets colder, decrease the rates of weathering. We might, therefore, if we're decreasing the rates of weathering, we're decreasing the removal of CO2 from the atmosphere. More is in the atmosphere, and therefore it gets warming. It reduces the amount of initial cooling. That makes it a negative feedback. But these are details which could be added to get those bonusy marks type things. Right. Question 4, which was the second question in the second part of the exam. So this was a question all about proxies. It starts out talking about CO2, but that makes it confusingly similar to the first question. This was not really about forcings or feedbacks. This is about proxies and the evidence we are expecting for climate change. So just looking at that first question again, this is not worth a huge amount, so not looking for essays on this. So the question and explain why CO2 concentrations measured from bubbles trapped in ice cores are not considered a proxy. Okay, so another way of thinking about that, you think about, well, what is a proxy? I mean, what do we mean by proxy when we talk about climate science? And then why is CO2 not conforming to that definition of what we're thinking of a proxy is? Quite a lot of you kind of did quite well on this question. There were a few people that kind of missed the some key parts. So this is some CO2 bubbles in some ice, and we're specifically looking at the CO2 trapped in the bubbles, not any of this other stuff for this question. And what we're really looking for is, a proxy. I mean, the thing that defines a proxy is that it is an indirect measure of something. Okay, and in this case, it's an indirect measure of some parameter of the climate system. So we're talking here it's a measurement that can be kind of calibrated to some other parameter. Okay, so CO2 is not a proxy because it is a direct measurement of the past atmosphere. Okay, we have little bits of the past atmosphere trapped, and we can directly measure its composition. So that means that it's not a proxy for CO2 concentrations. But some people did make the argument, and this was, I think, something I mentioned in the lectures, that you might even think of, actually, this could be a proxy, but it's not a proxy for CO2 concentrations, because it can't be a proxy for itself. But you might think that CO2 concentrations recorded in little pockets of the past atmosphere might be useful for a proxy of past temperature, because temperature and CO2 are so closely related through geological time that if we could measure just CO2, we could use that as a proxy for past temperatures. Okay, so you have a little bit of credit there if you said kind of why CO2 was not a proxy, but then said, yeah, but it could be if we're thinking about a proxy for something else, not CO2 concentrations. So this is a kind of it's not so much a trick question, but it enables kind of you to get those extra marks if you go that little bit further in your reasoning and thinking about what the question could be asking. Okay, so the next part of the question is much more substantial part. It's worth 40%. So we're basically just asking for some examples. So critically, question asks for 2 examples. So we need a proxy for sea surface temperature and another proxy for sea surface temperature. So 2 things required for sea surface temperature, and then an example of a proxy for land temperature. Okay, and then critically, the question really has 2 parts. It has give some examples of proxies and then describe how these work. Okay, so it's important that each of the proxies that you give, you need to give a description about how that proxy is used to reconstruct that particular environmental parameter. And there were lots of examples you could have used. Just whizzed through some here. One that quite a lot of you used was the biological assemblage of some marine fossils as a sea surface temperature proxy. So different types of marine organisms tend to live in different temperature waters. So if you find warm water fossils, then you can assume that the temperature was warmer in the past. And I think you could take it that little bit further when we're asking how are these used to reconstruct temperatures in the past, because you can say actually, rather than just say, oh, the warm ones lived in some warm water and the cold some different species lived in colder water, and we can say hot or cold, we can actually start to say, can we actually make a calibration curve of our proxy? So there's an example of that here. So the act of calibrating proxies against kind of modern conditions or kind of other proxies would be an important part of this question as well. Similarly, for another example might be oxygen isotopes, which are measured in the carbonate produced by these by some organisms in their shells or tests or skeletons. Now, I guess the mechanisms by which isotopes can fractionate between heavy and lighter isotopes, and that gives rise to a temperature proxy, is maybe a little bit beyond the scope of this course, but just broadly speaking, I mean, when you have more heavier of the isotopes, that tends to indicate colder conditions. And I guess that's the only really level I was kind of expecting for someone describing the mechanisms of oxygen isotopes. Obviously, if you went into the details of why isotopes fractionate, that would be fantastic. It would be very useful for you to have learned that for future courses. But some details would have been nice, but not entirely required. So moving on more towards the how are these proxies used to reconstruct the past, we need to understand, I guess I mentioned this a little bit already, we need to understand the processes in the modern world and how the relationship between kind of things like temperature or ice volume or precipitation, how they control how the proxy is recorded in the thing we find in the fossils or in the sediment. So basically, how do we calibrate our proxies? We also need to have some measure of how old the thing is that we found, either in a sediment core or maybe in some sediments on land or in kind of counting bacteriums. We need to basically, if we're trying to reconstruct the past, we'll usually have some kind of graph where we'll have some proxy reconstruction of the environment, temperature, salinity, precipitation, and we need to have some control on the age of our reconstruction. Okay, so that chronology component would have been a useful thing for you to put into your answer for this question. Okay, example for tree rings for the land temperature. Okay, again, thinking about how we use these to reconstruct. So you could explain a little bit about how this proxy works. So we have a large ring that indicates a warmer or wetter year. Colder rings are kind of like a thinner. Colder or maybe drier, or maybe some fire damage. Something that's causing the tree to grow not so well. But again, how these proxies are used to reconstruct, we can use counting them back to reconstruct the climate. We can overlap different sequences where we don't have trees that go back kind of continuously back in time. We can overlap one tree with another. So going into a little bit of the detail about how the chronology is constructed, a little bit of the detail about why different ring widths give what are resulting from different temperatures would be useful in constructing your answer to this part of the question. So those details about how proxies are calibrated, how the ages are constrained, that feeds quite nicely into the last part of the question, which was about what are some of the problems. Thought I'd just bring up this example, though, looking at the past sea surface temperatures, because a few of you made a mistake here. Well, not so much a mistake, but quite a few people mentioned that these annual bands in corals are used as a proxy for sea surface temperature because when it's warm they grow more. Now that's not strictly true. So while corals do sometimes have annual bands in as they grow, that thickness isn't really a very good proxy for sea surface temperature. Okay? It is sometimes used as a proxy for seawater chemistry. So the acidity of the ocean, for instance, can affect how dense the carbonate is when it's precipitated by the coral, but not so much sea surface temperature. The kind of proxies that we use in corals are more to do with the chemistry and the isotopes preserved in the carbonate. So things like the magnesium-calcium, strontium-calcium ratios and the oxygen isotopes are more often used as proxies in corals than kind of annual banding. So the last part of the question was about these kind of uncertainties or biases when we're more strictly when we're making these reconstructions. So basically the question asked is, what can go wrong? Why could we get the wrong answer? And there are kind of a huge range of things that can kind of go wrong. Now, there was a little bit of, I guess, wouldn't say confusion, but misdirection in some of your answers when you talked a little bit about why the measurements might be wrong or have large error bars on them. That's not strictly a bias. So our ability to measure something at high precision is great, but we would still be getting the right answer if we had big error bars on our measurements. Biases are really where our average estimate is being shifted away from the true value by something else that's affecting our proxy. Okay, so it could be that, for instance, the chemistry or the isotopes preserved in a coral skeleton or some foraminifera tests is affected by more than one parameter. So it might be dependent on temperature and ice volume, salinity, calcification rates, carbonate ion concentration, lots of different environmental parameters. So making one measurement and then making a temperature record would be kind of inaccurate, because if there were any changes in any of these other parameters during the time we were looking at, then they would affect our proxy record. Other kinds of biases are if we are trying to reconstruct the annual average temperature and our thing that our proxy is recorded again only grows in spring or summer, then we might have a seasonal bias in that we might not be recording the average annual temperature, we might just be recording the seasonal temperature. And that might change differently through time than the annual temperature. Other things that can go wrong are the principle of uniformitarianism might break down. So the present might not be the key to the past, or the past might not be the key to the present. Which way around that goes. Anyway, so that we might see in the modern ocean a really nice calibration between sea surface temperature and species assemblages of different kinds of forams, but then maybe back in time, those same species of forams might have had different temperature tolerances. They might have evolved slightly, and that means that our calibration might not be valid back in time. So those are the kind of things that can affect us in a bias rather than just having large error bars. Okay, so hopefully that will give you some idea about what we were looking for those exam questions, where you might have missed out on marks by not fully explaining something or missing out specific parts of the question. So yeah, so hopefully that's been useful to you. If it is not, then obviously, there we go. If you answered any of the questions from part D, then watch the next video, which I will link in the down in the description of this video somewhere. Anyway, okay, right. Yes, thank you for watching.